Hey everyone, welcome and thank you for choosing to spend your valuable time with us today. Today's webinar will be covering benchmarks with wolfSSL presented by wolfSSL software developer Jacob Barthelmeh. My name is Cameron and I will be moderating the webinar. All attendees will be in listed mode only. If you do have any questions, please use the Q&A box. We will host a live Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you all to follow us on Twitter. That's at wolfSSL. Also on our other social media channels. And feel free to email us if you have any questions. That would be facts@wolfSSL.com. And now I'd like to give a brief overview of the company before we move into the technical presentation. Today, wolfSSL secures over 2 billion connections, and we have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which who are engineers. This progress is, of course, supported by a strong partner network that we're extremely proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-178 support, FIPS certification, and a FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, a commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans all the way up to the 24/7 level. We also offer full service consulting. And yeah, now I'd like to turn it over to Jacob to talk about benchmarks with wolfSSL.
Thanks, Cameron. Yeah, for going through the benchmarks with wolfSSL, we'll be focusing a lot on the wolfSSL product itself and the application, and then the hardware acceleration that we've done on different devices. A lot of that being embedded, but also some on like desktop systems and with asynchronous crypto as well. We have a section about TLS benchmarks, how we went about collecting those TLS benchmarks, difference in Cipher suites, and then near the end we'll be talking about post-quantum benchmarks and a little bit of a roadmap of what we got coming up in the future as well. So besides the obvious reason of why to increase performance, some of the reasons that people go about using our hardware acceleration is to reduce the code size, actually. You see this a lot with like AES tables, where someone can offload the AES tables to the hardware. That then frees up a lot of memory that they can use for other operations or other code. It increases the performance for like user experience as well. User interfaces can be more responsive while still being secure. And faster speeds can also improve response time in critical real-time operations. One of those is like if you're thinking about a lot of these newer vehicles have automated brake systems. If the brake system is communicating to some of the central processing via a secure channel, you want it to be braking as soon as it sees something rather than trying to brake after it already hits it. So faster speeds can be very critical in some use cases. This gives a little bit of an overview of the wolfSSL benchmarking history. We partner with NXP STM32, and that shows one of our first hardware acceleration offloads, excuse me, was the MMCAU back in 2012. That was with NXP. We also have the Intel ESNI that we did in 2014, TI Texas Instruments in 2015. One of the other big ones to call out here was the SP edition in 2017. SP stands for Single Precision. It was done by our engineer, Sean Parkinson. Now I'll go into a lot more detail about SP in future slides, but it greatly increased the performance of asynchronous operations. I think ECC, RSA, and DH operations. We also have Xilinx Petalinux on here. We've done a couple of Xilinx hardware accelerations, most of them making use of the Zil Secure library through different operating environments. One being Petalinux, done with FreeRTOS, as well as bare metal. And NXP CAM in 2018, multiple different NXP devices with that NXP CAM. We also work with stuff like, I think, EdgeLock with NXP. On some of the newer stuff, like the NXP SE050 done in 2021. One of the new ones that we did this year was OpenCL. That was actually about 3 weeks ago. We did it was roughly like a proof of concept showing the AES encrypt running with CUDA. And we've done a lot with Espressive. We have RISC-V that came in 2023, and a lot of other Espressive stuff that have been happening recently in the last couple of years. So what is the common metric used to measure performance? With crypto operations, it's usually megabytes per second. That's what our benchmark application displays by default. It also, when available, displays cycles per byte. That's how many cycles it takes to be able to encrypt a byte of data. The lower the number, the better. Some of them actually get underneath 1 cycle per byte, which is just pretty impressive. Another measurement used is operations per second. A lot of times this operations per second is talked about with asynchronous operations. So you think of like a RSA sign. How many RSA signs can it do per second? How many ECC signs ECC verifies? And then the average verify sign time with public keys, that goes back to the operations per second, but it's the average over usually over a second. The average over a second gives yeah, basically just the average of how long it's going to take to be able to do an ECC sign or verify. With TLS, this is on top of the crypto layer. Usually what's talked about for metrics is time per connection. This is how long it takes for the handshake to be established. So you can think each time you try and connect to another device or a peer, it's how long it takes for that connection to actually get established. And then throughput is what's happening after the connection has been established. So that's going to be more benchmarking like the symmetric key operations like AES GCM and how fast those are running inside of a TLS after the connection has been established. So that goes through a little bit about the performance history in wolfSSL, showing that brief timeline and why people would be interested in performance. This is talking more about like the benchmark application that we bundle with the wolfSSL library. And this is it's a really simple benchmark application to run. Anyone on a Unix system can run it very quickly. I'll actually go through a demo here in a bit of how you can run the benchmark application after downloading wolfSSL. And we've ported it to many different devices. We've ported it to Windows. It's dead simple to run on Unix-like systems. We've also been able to run it on a lot of embedded devices, as I'll show later on with benchmark numbers that we've collected using it. And it's built by default with auto tools when just doing a configure make. To run the benchmark application, you'd want to be looking in the directory wolfcrypt benchmark. So you just run wolfcrypt benchmark. And there's many options available for running individual algorithms and even Japanese translations. All of the options can be seen with a -H flag. So we're constantly expanding on this. If you want to keep up to date on which options have been added or which options are available, -H is a good way to see. With embedded devices, you want to use the macro bench_embedded. This decreases the size of buffers used for resource-constrained devices, and it can take forever for some of these more edge IoT type of devices to run an RSA operation, or well, less so an ECC operation, but it can take quite a long time for RSA operations. So this bench_embedded macro kind of decreases the number of RSA operations that's going to run before it gets its average. The benchmark application can also be executed from an external application by calling the function benchmark_test from wolfcrypt benchmark benchmark.h. You can also set up configurations for how you want the benchmarks to run. There's even individual algorithm functions that you can call from benchmark.h. So you can do quite a bit with if you want to set up your own application that's then making use of the benchmark code without actually like running the default benchmark application that gets included in wolfSSL. This gives a bare example of a printout after running the application. So in this one, I configured with enable SP, enable -SP -asm, and those enable options are recommended for speeding up the RSA, ECC, and DH operations. By default, they aren't turned on, at least not the SP -asm, the assembly optimizations, and that's because we target resource-constrained devices. This SP-asm increases the code size, but the trade-off is that increased code size, you get an exceptionally faster asynchronous operation. All right, so I'll switch over to my terminal here and show how simple it is on a Unix-like system. So in this directory, I have the wolfSSL 5.7.0.zip. This is the same zip that you would get from the download page from wolfSSL.com. And this is running on a Mac system, so you can think of this as like any Unix-like system. It'd be the equivalent steps that you do on Linux as well. So if I unzip it, go into the directory that it created, and then I like to build with enable SP-asm, because it turns on the assembly optimizations for RSA, ECC, and DH, and then make. And this is with a system that you have auto tools installed on. A lot of Unix-like systems, that's pretty straightforward. Like Linux systems, it'd be a simple sudo apt get install autoconf. It's also assuming that you have make on the system, which comes by default on a lot of Unix-like systems, and the GCC compiler, obviously, or Clang. So after it's ran make, you can do wolfcrypt benchmark -h, gives you all of the options that are available. You can select specific ciphers that you're interested in, measure specific key ECC sizes, output and CSV, all kinds of different options that we have available. I'll select one here. A lot of times people are interested in AES-GCM, so you can do -AES-GCM, and it gives you benchmark values for AES-GCM. This was without the AES-NI enabled, so you can get even faster performance if doing something like enable Intel ASM and enable AES-NI. But the equivalent of that for ARM systems is going to be ARM ASM. That would give you faster AES operations on an ARM system if you use enable ARM ASM. So yeah, that's just demonstrating how quickly you can get up and running with benchmark numbers on your device. If you're curious how wolfSSL compares to what is currently being ran, or want to get rough ideas of how fast it would be running on your system. Back to the other slide. Okay, so building wolfSSL for performance. You saw earlier the enable SP and enable SP ASM dash ASM flag, and enable ARM ASM and enable Intel ASM. Those are some of our big, I guess you can call them big flags for performance enhancement. And like I'd mentioned before, our default build is focused on security, side channel resistance enabled, and more geared towards the middle for code size. With the SPASM and enable ARM-ASM or enable Intel-ASM, depending on if you're on an Intel or ARM device, it'll increase the code size, but greatly increase the performance. One of the other performance optimizations is FP_ECC. That helps by caching some of the points in the calculations done with ECC operations. So if you're using the same key over and over for like a assigning operation, for example, it would help cache the ECC points so that it speeds up as you continue to use the key over and over again. So single precision was developed by our wolfSSL software engineer, Sean Parkinson. It increases performance for commonly used key sizes. It's where its single precision is focused on specific key sizes. Those key sizes are ECC NIST 256, 384, and 521. They're common key sizes used in the TLS protocol. They're also common key sizes used in other protocols as well. It also speeds up RSA 2048-bit, 3072, and 4096, and some of the DH operations as well. Speeds up ECC key generation, and when using auto tools, it can be built with enable flag, enable -SP. The assembly version of it is enable -SP-ASM. We have speedups for both Intel and quite a few ARM series as well. Some of those ARM series is the Cortex-M. We also have assembly speedups for ARM Thumb, and then pretty much all of the ARM V series. I believe it goes all the way back to ARM v5, maybe even ARM v4. One of the more recent ones that's used is the ARM v8 series, though. If building on a system that doesn't have access to AutoConf, or building using an IDE and something like a user_settings.h file being included for the macros defined, the macros for SP enablement would be the following: the wolfSSL have _SP RSA for RSA. There would also be the wolfSSL have _SP_ECC for ECC. This shows there's the wolfSSL _SP small build. This was to have the single precision, but try and reduce the code size. Obviously, you get a reduced performance with this wolfSSL _SP small, but it trades at reduced performance for also having reduced code size. There's the wolfSSL _SP ASM, turns on the assembly optimizations, and then you have a different assembly ASM flag for each of the different architectures that are supported. For example, this ARM64 _ASM or the ARM Thumb _ASM. So that's how to run the crypto benchmark application that's included with wolfSSL. A little bit about building wolfSSL for performance optimizations. Next is some of the hardware acceleration that we've done and some of the values that we've collected on the embedded devices that we've offloaded for hardware acceleration. So I've done quite a bit with STM32, the STM32 F2 series, F4, F7, a couple more in addition to those series that we've done with STM32 as well. And this shows just how much of a performance can be gained when turning on this hardware acceleration. So you see for AES GCM, before with just software only, it was actually below 1 megabyte per second for how fast it was. It was encrypting, decrypting, and then accelerated. It's up over 6 megabytes per second, so that's well over 6 times. SHA-256 operations, you see more than double the speed. And then for RSA operations, you also see a decent increase in speed, and ECC operations, quite a significant increase in speed. And this was on the STM32F777 that these were collected on. We also have support for offloading the hardware acceleration on Renesas. This shows Renesas Synergy DKS7G2 benchmark numbers. And we've done work with Renesas TCIP. This Renesas, some of the Renesas stuff we've done actually incorporates at the TLS level as well. I don't have those benchmarks collected here or displayed here, but we have benchmarks displaying like the Renesas TCIP at the TLS level if interested in seeing those. But yeah, it shows almost double with the AES 128 CBC. And again, significant improvements on the asynchronous operations when you offload it to hardware. And we've done a lot with the NXP devices. One of the, I guess, relatively recent ones was the K82. A large number of the NXP devices supported also have examples along with IDE projects. So in our main wolfSSL directory, there's this IDE, all caps IDE directory that has a bunch of subdirectories for different IDEs that we've got example projects for to try and make it easier for people to just get up and running really quickly with wolfSSL on whatever IDE they're potentially using. So if you're using something like CodeWarrior, we have a lot of examples for CodeWarrior, MCU, Espresso, and there's other ones in there as well. Xilinx SDK. So Xilinx SDK one is for Vitis, but yeah, there's quite a few in there if you're looking for a starting point with wolfSSL on a specific IDE. And anyway, with the K82, back to the benchmark numbers here, the K82 had a significant improvement with AES operations, well over 12 times. And then SHA operations, again, you're seeing about double the speed with SHA operations. There's too many hardware accelerations to go through in the time that we have, but some of them are like Coldfire, Cavium, the Microchip PIC 32, Nordic NR F51. We've done stuff with the Atmail, NXP Cam, like I mentioned before, multiple devices, IMX6, IMX8, RT1170. So quite a few different IMX devices with NXP Cam. And yeah, recently there's the Espressive stuff and the CUDA that we've done a proof of concept with. So for ARM hardware acceleration, you can enable the ARM v8 crypto extensions. They actually have a couple of assembly instructions specifically for speeding up AES and for SHA-256. Use of those crypto extensions is enabled with --enable-arm ASM. using enable-armasm also enables the neon instructions. And those are instructions that are able to handle like large vector operations better. And they're used for speeding up cha-cha-20 as well as poly 1305. Then for the ARM assembly with the single precision, as we mentioned before, it has an enable-sp-asm. You don't have to specify if it's an architecture or not with the enable-sp-asm. The autoconf logic figures out what system is running on and applies the right macros. So you just need the enable-sp-asm, and it'll speed up RSA, ECC, and DH on ARM hardware. These numbers were collected on a high-key maker board, so it's a relatively beefy board, and I wouldn't consider it too much of an IoT because it's actually got a version of Linear Linux running on it. But it's running at 1,200 megahertz, and this was with wolfSSL 5.7.0, so the most recent release out. You can see the RSA operations significantly faster with enable sp-asm, DH operations and ECC operations as well, all across the board significantly faster. And then with the symmetric key algorithms, you can also see that AES operations are significantly faster. In the last couple of years, we had a refactor to our AES GCM with ARM v8, which versions, I believe it was around 5 point, I want to say 5.5, but I can't remember exactly off the top of my head. But yeah, in the last couple of years, it was increased from 300 megabytes per second to up over 500 megabytes per second. So we're constantly trying to squeak a little bit more out for performance. And then you can see that neon instructions are used as well as assembly versions with cha-cha and poly 1305 to help speed those up as well. The other big desktop system is with the Intel hardware acceleration. The configure options when building with auto tools is enable Intel ASM. That tries to add in all of the Intel speedups. And then there's also the enable AES-NI. AES-NI is specific to the AES operations. With this enable Intel ASM, it doesn't only enable like symmetric key algorithm and performance enhancements, it also enables use of RD-RAND and RD-seed, which is nice for having more secure sources of entropy. So when using the flag enable Intel ASM, it automatically also makes wolfSSL try and use RD-RAND and RD-seed. We use the AVX instructions, advanced vector instructions, for increasing performance with operations like SHA-256 and cha-cha-20 and poly 1305. You can think of these ones as the equivalent of the neon. That's an oversimplification, but they're used in a lot of the same way as the neon instructions were in with the ARM architecture. We also have the bit manipulator instruction sets. Those are used potentially in some of like our rotations and more like in our miss.c file. This is a comparison with the asymmetric algorithms. So you can see it's a significant increase when running, significant increase in performance when running with the hardware acceleration turned on. And then this was on a 2.4 gigahertz 8-core Intel Core i9. So you can see it's, I'd say roughly 6 times with the RSA 2048 public key. And then also, this is the symmetric key algorithms. Again, a significant increase in performance when turning on enable-Intel ASM and enable-AES-NI. So with GCM, that live demo I did before, I didn't have the enable TLS and enable ASNI, so I got right around this 144. If rerunning that with the enable TLS and the enable ASNI, you would see almost 4 gigabytes per second, so 4,708 megabytes per second versus the 144 with software only. So one of the other hardware accelerations that we have is offloading to GPU. It was introduced approximately 3 weeks ago on GitHub pull request 7436. So it wasn't out in 5.7.0, but it is going to be out in our next release. And it's kind of just like our proof of concept, I guess you would call it, for wolfSSL being able to run on GPUs. GPUs are set up more for parallelization over fast serialized operations. So the our first proof of concept on it is going to be slower than what it would be running on the CPU, just because we weren't massively parallelizing it. It was just showing, the AES encrypt running on a GPU. And this is the configure that you would currently use for it. Don't necessarily need the enable all and the disable serial monitor, but this gives you a good starting configure for if wanting to try it out. And right now it's enable -CUDA. You got to set the compiler and then a couple of the LD flags for linking against the right libraries. And this one, it was on an NVIDIA H100. This is the AES 128 CBC encrypt on it. As you can see, is pretty slow, but that's kind of expected since it was running just an AES encrypt on a GPU not in a massively parallelized kind of fashion. It was just running through it. And then this is the AES 128 decrypt on the software, or the software implementation of it running on the CPU. Another thing that we've set up for performance enhancements in previous projects was a dispatcher. This dispatcher did is it controlled the CPU device offloaded to based on heuristics that can be preset. It was initially developed to be used for offloading ECC operations to a DSP. So in the use case, they had tons of ECC operations coming in, and they had a couple of DSPs and also the main core. So they wanted to be able to basically route which DSP, which core the operation was going to be sent to and ran on. It included the handling of priority of operations. So there might be specific operations that come through that have a significantly higher priority than others and require the verify operation or the ECC operation in general to be done quicker than what other operations would do. And again, that comes back to like if you have something like a system critical like breaking signal coming through that needs to be processed a lot sooner than something like, hey, the weather is going to be nice, or what music channel to be on. So this dispatcher can handle the priorities that come in. So that's a little bit about the hardware acceleration and some of the benchmarking that we've done. That was all. A lot of that was all at the crypto level. Next is going to be a little bit about like the TLS benchmarks. So in addition to that benchmark application that is included with wolfSSL's bundle, we have a couple of ways to be able to actually benchmark the TLS connections as well. There's a script located at scripts benchmark.test. There's also the TLS_bench located in directory examples benchmark. And then the third way to be able to do it is from our example client and example server that are bundled with wolfSSL. You can use a dash lowercase b for doing a number of connections in a benchmark. You can also use a dash capital B for measuring the throughput. So there's a couple of things that you're measuring with the TLS benchmarks. One of those is time per connection. The other is how fast that can be transmitted back and forth after the connection has been established. This breakdown between different Cipher suites, or a couple of the Cipher suites, is in 1.3 and 1.2. And client side, first two, Cipher suites here, was TLS 1.3. You had the TLS 1.3 AES-GCM, and then comparing that to Cha-Cha-20 Poly 1305. You can see it's relatively close. This was with all of the assembly turned on. Without the assembly turned on, Cha-Cha-20 Poly 1305 would be faster, but since it was on an Intel device that had the AES and I accelerations with AES-GCM, it was pretty on par, somewhat just a little bit faster with the AES-GCM with AES and I. Then you go down to the TLS 1.2 here, and you can see most of the time it's going to be a slower throughput than it was with a TLS 1.3 connection. And that's just due to how TLS 1.3 is, the differences between TLS 1.3 and TLS 1.2, that is. This one was a difference between the time per connection for the same Cipher suites. I think there was some, I guess you could say, poisoning of the benchmark collections here due to like overhead of the actual sockets themselves and some of the overhead in the benchmark application that was being used. But you can see they're relatively on par, which you'd expect the TLS 1.3 to be just a little bit faster than the TLS 1.2, but otherwise you would expect these to be on par because they're using the same like ECC operations. So they're going to be close to the same with, even though it's listed as Cha-Cha-20 and versus AES-GCM, they're using both the same ECC operations and RSA certificates. And this is with ECC certificates, and it was obviously a little bit faster than it was with RSA certificates. You can see here, this one, RSA, time in milliseconds, average time in milliseconds was up here, a little over 1.5. And then this one, it's hard to see on this, but it's a little bit less than it was before, as far as the average time per connection in milliseconds. So that's how you would go about doing TLS benchmarks, at least with the applications and the scripts that are bundled in wolfSSL. The next section covers a bit of our asynchronous code, as well as wrapper benchmarks. And with those wrapper benchmarks, I'm going to be talking about like our Java wrapper specifically. So asynchronous crypto is often used in like large enterprise servers that handle many verify sign operations a second. You think in amount of like millions or billion, even billions potentially connections being handled. wolfSSL supports Quick Assist as well as Cavium Nitrox. It was an add-on feature that we had. I believe it's recently been open sourced. You can find it up on our GitHub repository with wolfSSL, and it's enabled with -- enable -async crypto. The benchmark values on the next slide were performed on an Intel R Core i7, and they were collected with a earlier version of wolfSSL. It was actually back in wolfSSL version 3.15.7. But where asynchronous crypto shines is with asymmetric operations per second. You can see with the symmetric key operations, it's relatively close to what it was with like the software ASNI. Even a little bit worse, honestly, in a couple of cases. But with the asymmetric operations, it's significantly faster. So you're looking at the RSA public verify operation or sign operation, and yeah, it's more than 10 times, at least for the sign operation. And that's relatively the same with the ECC operations. Not quite as significant as a jump, but still better performance with the quick assist when handling a lot of connections or a lot of operations. It definitely can speed up the performance. So one of the wrappers that we have is JSSE. This is a Java wrapper. JSSE is often used with like Android systems or anywhere basically where they're wanting to call some kind of interface for using standard APIs and whatnot for using TLS. And I did some JSSE benchmarking between the native wolfSSL. So native wolfSSL is just the C implementation versus wolfJSSE, which is our JSSE implementation, and the default Sun JSSE, which is provided on by default on a Mac. And you can see the average time per connection with the client configured with C only. So this is just our basic wolfSSL C library, no Java. It was around 9.6 milliseconds. And then with Intel ASM plus SP plus SPASM was around 7.3. This was also with an older version of wolfSSL, so it doesn't quite match up with the Intel, and on a different hardware, so it doesn't match up exactly with the Intel benchmark values I showed previously. wolfJSSE client software only was 10.9. wolfJSSE client with SP plus Intel ASM was 8.4. So you can see there's around 1 millisecond overhead when going through JSSE versus going to the native C implementation. And then comparing that to the Sun JSSE provider, that was around the default on the Mac system was around 13.34 milliseconds for the average time per connection. So switching over to use Wolf JSSE would save you right around 5 milliseconds per connection. And then this just gives a better visual of the differences between the respective builds. One of our new products that we've come out with recently is wolfHSM. Why I'm adding this in here with the wrappers is it's using the tri-core hardware acceleration. And yeah, it can make use of the tri-core hardware acceleration. We've got some benchmark numbers to come, so it's something to look out for. It's a good fit for quite a few use cases where you need like a software kind of version of an HSM or just a software interaction between an HSM. wolfHSM is a good fit for those cases. So the last thing we'll be talking about is before going on to questions is the post-quantum and a little bit of a roadmap about what we'd like to do in the future with performance optimizations. And this gives one of our algorithms benchmark values. So this is specifically with Kyber. Kyber is now bundled with the default wolfSSL bundle as of wolfSSL 5.7.0. Can enable Kyber with --enable -Kyber and enable experimental has to be done as well, because right now we consider it experimental. So --enable-experimental. And that's our own implementation of Kyber. This gives some of the current benchmark values of it, and also on the bottom here, a average time connection using Kyber as the key share with TLS 1.3. So it's around 1.43 milliseconds for time per connection. So a little bit about what's on our roadmap for performance optimizations. We're going to look at more about ARM64 assembly, just seeing if there's more that we can do with the ARM64 assembly that we currently have. Seeing a little bit about increasing the SP small performance. So right now, it's a little bit I guess you could say quite the contrast between performance of just regular SP and the SP small. So we're going to be taking a look at that to see if there's something we can do there for increasing performance. PowerPC 32-bit performance optimizations, more on the RISC-V. We have RISC-V hardware acceleration already, but there's more that we can do with RISC-V. Then async multi-threading and non-blocking. So we have async in at the moment, but there's more platforms that we could potentially do that with. One of them that comes to mind is we handle all of like the NXP cam operations in a synchronous manner. We could potentially do asynchronous and more non-blocking there. We also have NVIDIA Bluefield hardware encryption as one of our roadmap items. And like usual, we like to hear feedback that people have, what they're looking for performance optimizations. So if you have a request or something that you're interested in seeing performance optimizations on, you can send it to fax@wolfSSL.com. And I guess with that, I'll go ahead and open it up to the floor to see if there's any questions.
Awesome. Hey, thank you, Jacob. I do have one question here. Is an LMS or an XMSS implementation on the roadmap for post-quantum? If so, when is this expected?
So the answer is yes. We're in the process of actually getting that into our master branch. So it's near the tail end of being done. We have LMS and XMS by using liboqs at the moment. Well, not liboqs. I can't remember. It's Cisco. So we used an external for LMS and XMS currently, but we have our own implementation that's coming in the main wolfSSL branch here in a bit.
Awesome. Does using the FIPS code base affect performance?
So with FIPS, it's a locked in at a specific version of wolfcrypt. There are FIPS certifications that we've done in the past that use the hardware acceleration. You just got to make sure that when you take your OE through the FIPS certification process, that you're using like the hardware acceleration that you want versus the software implementation. And so in that regard, it can affect performance, but there are ways to be able to use the hardware acceleration as well with FIPS.
Ready. Next question is, would the recording of the webinar be available to download? I will be sending out an email with a copy to everybody after this webinar, and if you'd like slides as well, we can provide those. And then next here, is the hardware acceleration for RISC-V, or is there hardware acceleration for RISC-V?
I see. Yeah, we've done hardware acceleration for RISC-V. There's definitely more that we can do there. More algorithms. Yeah, so it's on a roadmap to tackle more RISC-V integration, but we do have some available currently.
Awesome. And does the SP performance enhancements affect side channel mitigation?
Yeah, so that's one of the things is when you do side channel mitigation, it does affect the performance some. We by default have side channel mitigation turned on. Using the SP implementation is actually going to be one of the more resistant to any side channel attacks. So right now, if you enable SP and then enable SPASM, that is with side channel resistance also enabled by default. So no, the SPASM is not going to lower the resistance to side channel attacks.
Awesome. Looks like that wraps up our Q&A section. Thank you, Jacob, for hosting an informative webinar. Oh, actually, I got one more that came in here. For those customers that do not run configured tools, where can they find the corresponding preprocessor for a specific option, e.e. enable SP and enable SP ARM-HSM?
Sure. Yeah, our manual has it, but one of the great places to look at first is to see if we have um, a project already in the IDE directory for the IDE that you're trying to build for example, like CodeWarrior. And that's a good starting point. A lot of those that we're doing recently have the SP stuff. But if it's not in there and if it's not apparent where it is, we're more than willing to help with anyone that's trying to get benchmarks running on a embedded device. So if you reach out to like support@wolfSSL.com, we can usually point you to the right ones if it's not apparent which ones to use.
Awesome. Thank you, Jacob. And then, as I mentioned before, I'll be emailing out copies of the webinar and can provide any PDF slides upon request. You can keep up with all of our events, our blog posts, and other wolfSSL updates by following us on X, connect with us on LinkedIn, and subscribing to our YouTube channel. If you do have any questions at all that come up after this, don't hesitate to shoot an email over to facts@wolfSSL.com. We're always happy to help. And thanks again. And we look forward to seeing you next week for enhanced security SM ciphers integrated with wolfSSL with Sean Parkinson.